Welcome to the first of a series of lectures in Linear Algebra module, Math 1503, and in the Extended Science module, XAT 1503. And we will be dealing with the introduction to systems of linear equations, which can be found on pages 1 to 9 in edition 11 of your prescribed textbook. We started with the definition of linear equations, where we define a linear equation in Rn space as follows. A1 x1 plus a2 x2 plus a3 x3 plus up to an xn equals b. So the coefficients a1, a2, a3 up to an are all non-zero. You will notice that all the x values, x1, x2, x3 up to xn, all have degree 1 or power 1. And this is why this is defined as a linear equation, because the power of each of the variables xi, I going from 1 to n, is 1. So let's have a look at an example of a linear equation in R2. So ax plus by equals 2. Right, that would be an example of a linear equation in R2. R2 because there are two variables, x and y. The coefficients a and b are non-zero, and each of the variables has degree power 1. We do not write in the exponent 1 or the power 1, but I'm just showing you that that's why this is linear. And then an example of a linear equation in R3, that's three-dimensional space. So we are expecting three variables, ax plus by plus cz equals any other constant. Right, so now we have 1, 2, 3 variables. Therefore, we are working in R3, three-dimensional space, and once again, the coefficients a, b, and c have to be non-zero. And please notice again that the exponents, the powers of the variables x, y, and z are 1. All right, so then in your first assignment, we also ask you to classify whether the equations are linear or non-linear. So let us have a look at when certain equations are non-linear. Okay, well, first of all, as I've mentioned with my other examples, that all the variables have to occur to the first power. All right, so can you see then that something like x plus 3y squared equals 4 is non-linear? And that is because the power of the variable 2 y is 2, and we said that it had to be 1. So that would be an example of an equation which is non-linear. Another example would be there where there's a trig function involved. So something like sine x plus 3y equals 2, or any trig functions. When there's a trig function involved, then it is non-linear. Or if there's a log function involved or an exponential function, such as log x plus 2 to the y equals 3, for example. So you've got a log function, you've got an exponential function, therefore such an equation is non-linear. Right? Another example is where you have products of the variables. For example, 3x plus 2xy minus 5. So now we have a product of two variables, so the equation is non-linear. Let's take another example where we have roots. Root x1 plus 2x2 equals negative 1. So where there's a root involved for the variable, the equation is also said to be non-linear. So there's some classifications then. The power may not be greater than 1, trig functions, log functions, exponential functions, products of variables, and roots of variables makes the equations nonlinear. A homogeneous linear equation is a linear equation in which we have the linear combination of the variables with their coefficients, but it is equal to 0. So as we had in the defining equation, this was equal to b, b representing any constants. Well, now we've got that it has to be equal to 0 for it to be defined as homogeneous. So, for example, when you have x plus 3y, that's linear, and it becomes a homogeneous linear equation if I set it equal to 0. Right, let's chat a little bit about solutions of systems of equations. So a system of equations is when you have more than one equation to solve for the variables. When we speak about the solution to the system of equations, there have to be two requirements in order for that element to be a solution. The first is that the element has to have the same number of coordinates as the number of unknowns in the system. So if your system involves two unknowns or two variables, then your solution must also contain two variables. So if you're working in R2, your solution has to be in R2. If you're working in R3 in your system, then your solution has to be in R3. And then the second requirement for the element to be a solution is that your element must satisfy all the equations in the system. That means that if there's 3 equations in the system, that your element has to satisfy all 3 equations simultaneously. So even if it satisfies 2 of the equations, for example, equation 1 and equation 2, but then doesn't satisfy equation 3, then it is no longer a solution to the system of equations. I've missed a slide. That's a pity. All right. Let's have a look at what is the difference between a solution set and a general solution. Now, in terms of your study guide, these words are used interchangeably. So a solution set is referred to as a general solution. But I would like to show you what the difference is now between the way I'd like you to express your solution set to an equation and the general solution to an equation. So let's, for example, take the equation x plus 2y minus z equals 3. Well, first of all, can you see that this is a linear equation and it is an equation with 3 variables? In other words, we expect our solution to be an element of R3 with 3 variables. So in this, when we solve this equation, let's start off by looking then at the general solution first. All right, so the general solution would be, we've got 3 variables. So we're going to express x or y or z in terms of the other variables. All right, in order to do this, I'm going to let y be equal to s, which is any real number, and I'm going to let z be equal to t, which is any real number. Now we give these 2 variables a very special name. We call them parameters. They can take on any variable. All right, now we're going to rewrite the equation. So you'll see from the equation that x is equal to negative 2y plus z plus 3. All right, that is making x the subject of the formula. We get x equals negative 2y plus z plus 3. In other words, what this means then is that x can be rewritten in terms of the parameters s and t as minus 2s plus t plus 3. Right? So now we have the general solution. The general solution can now be written as x is equal to minus 2s plus t plus 3, y is equal to s, and z is equal to t. And this is now referred to as the general solution where s and t are your parameters. Okay, so that is how you set out the general solution to an equation. Now we use the same equation, but this time I'm going to do the solution set for this equation. All right, so in the solution set, we have, let us just go back to the general solution, because I want you to see that when I now write out the solution set, okay, I'm going to use this, but do you see that I now have to express my solution in set notation? So I'm going to write my solution as a set as follows. Open up a set of brackets, which is what we use for sets. We've got 3 variables, so it's an element of R3, so it's a set of all solutions of the form x, y, z, such that x is equal to minus 2s plus t plus 3, y is equal to s, and z is equal to t. And there we have a solution set, and we can close our curly brackets. All right, so there's your difference then. On this sheet, you have what's called the general solution. And on this sheet, I've shown you how to rewrite the general solution as a solution set. And we should always specify that S and T are our parameters. In other words, that they are elements of real numbers. So in the solution, when you're considering a system of equations, we need to look at this. Here's an example of a system, right? As I said, you can get more than 2 equations to form a system. So here I've expressed a system of 3 equations, 3 unknowns, x1, x2, and x3. We said that an element has to belong to the R3 space if there are 3 equations. Right, so I'm happy then that 1, 2, negative 1 is indeed an element of R3. The second requirement is that this element has to satisfy all 3 my equations simultaneously. So let us test to see then for which values of A is this element, 1, 2, negative 1, a solution to the system. So let's start off with equation 1. And we're going to substitute the element in there. So remember, the first variable, 1, is your x1. Your second, your 2, is your x2. And your 1 is your x3. Right, so let's replace it then and substitute. So x1 is 1, x2 is 2, and x3 is negative 1. Right, now test. According to equation 1, that should be equal to 0. Well, let's see. It's 1 minus 4 plus 3. Yes, that is equal to 0. So equation 1 has been satisfied by this element 1, 2, negative 1. However, this does not prove that we have a solution to the system. We need to use 1, 2, negative 1 in equation 2 and in equation 3 to find out what the value of A is if it is to satisfy all 3 our equations. Right, so let's continue then and substitute further. So now I'm going to substitute into equation 2. So I have x1 plus A times x2 is equal to 3. Right, that gives me 2A is 3 subtract 1, 2. A is equal to 1. So this is what equation 2 gives us, that A should be 1. Right, let's proceed with equation 3. So we've got x1 is 1. Then we've got x2, which is 2. Then we've got bracket A plus 1, x3, and that must be equal to 1. All right, proceeding with the solution, we get 3 minus A minus 1 equals 1. Now, if you solve for A, you get negative 1 on this side, and so A is equal to 1. All right, this is good news. From equation 2, when we solved, we got A equals 1, and from equation 3, A is also equal to 1. Therefore, the answer to this question, for which values of A is this a solution to the system, the answer is A equal to 1. Why? Because first of all, it satisfied equation 1. Then we tested if it satisfied equation 2, we would get A equal to 1. Then we tested when it satisfied equation 3, A is also equal to 1. Because these two values of A correspond in equations 2 and 3, we can say that A equals 1 is therefore the correct answer to example 1. Then I'd like you to also look at example 2, where I've taken the same set, but now I'm going to change it a little bit, and I'm going to change one of these values. All right, so it's still going to say for which values of A is 1, 2, negative 1 a solution to the system, but I'm going to change this question here, equation 3, I'm going to change to a 2. All right, so that now becomes my example 2. All right, so what you're going to do is you're going to test A, and we already know that equation 1 is satisfied. Now, if you test equation 2, you get 1 plus 2A equals 3, which gives 2A is 2, which gives A equals 1. Right, so we know that that is true from the first example 1. Now, look what happens when you test equation 3. You get 1 plus 2 plus A plus 1, negative 1 equals 2, right? So you get 3 minus A minus 1 equals 2. This time, you get 2 minus A equals 2, minus A is 0. This time, you get A equal to 0. The point I'm trying to make with this example 2 is that now if I had exactly the same question for which values of A is 1, 2, negative 1 a solution, because you are getting two different values for A when you substitute it into equation 2 and into equation 3, your conclusion is that there is no value for A that satisfies this solution. Can you see that you can only get a value for A if all three equations in your solution system are satisfied? And because these two do not match with each other, our conclusion is that there are no values for A satisfying this equation. All right, so now you should go and attempt some of these questions from your textbook and from your study guide. And I hope this has assisted you with assignment 1. Good luck.